All right, so this is actually going to be going backwards from what we did yesterday. And I know you're not finished with yesterday's activity, but you're going to get a decent amount of time to work today to go back and finish that activity. And then when you finish it, you can come and check answers with me. So there is a PowerPoint for this. I'll post it to Classroom if you want to look at it to supplement my own examples and kind of show them. But we're just going to fill in these blanks in your notes real quick. The two kind of key things here says implement each minturn in the logic expression with an AND gate. Okay, so in this first example, there are 3 minturns, and it's going to take AND gates to create those minturns, those combinations. Okay, and then to get them to come together to make the full expression, we're going to use OR gates. Because those sums, those pluses, really mean to OR. All right, and so we're going to design a circuit. When I look at these minturns, I see A, B, C, and D, B, C, D, B, A, B. So I see A's, B's, C's, and D's, nothing else, right? I'm going to pick out 4 good colors for myself. Kind of a blue, a green, a red, or I don't know, orange, red. Is that fine? I have darker red. Trying to get some contrast. Okay, so I need signals. If I'm going to create a circuit with gates and stuff. I need signals or lines that represent A, and I also need a line that would represent not A. So I'm going to kind of start over here on the left. I'm going to give a little space between the letters. I'll show you, just give you a preview. I'm going to have like a line, just a little short line, and then an inverter symbol. And then I'm going to make like a detour or a bypass around the inverter. And that is going to give me the ability to kind of grab either A or not A. Is that okay? Like this right here, that wire would be grabbing A. This wire is now not A. So I'm going to do that with A, B, C, and D, with all of them. So, and then from there, I'm going to be able to grab whatever I need. So I need to be able to grab not B and also B. And I just thought it might be helpful to have them in different colors. So I've got C, goes through an inverter, becomes not C. Or we can bypass the inverter and have C. And then same thing with D. And if you want to label them all, you can. So that's D. That's not D. I don't know. I didn't last time when I did it with the other class, but if you like that. There you go. Okay. You guys need a second to catch up your drawings? Where's my mouse? So now, I'm going to make each minturn. So I'm going to also, just because I can, make it easy. You don't have to have all the color coding like I do. I have this minturn with 4 different inputs, a combination of 4 very specific things. There are, in existence, AND gates that I'm going to make kind of a longer line than my AND gate's really going to be, so you can see what it's going to look like this. There are AND gates that exist that are 4 input AND gates, and the symbol would look like that. And so I'm going to go ahead and just assume that I can use a 4 input AND gate, and then I'm going to grab these things, I'm going to keep my colors, and I'm going to feed in this exact combination into my AND gate. And if I do that, that is how I'm going to create the signal of not A, B, not C, D. Okay? So I need not A, which means I'm going to grab the inverted A right here. And then I need B. So kind of coming this way, I'm going to take this. I'm going to try to keep everything nice and vertical and horizontal. And then the third input is going to be not C. And then the last one is D. So an AND gate is going to create the product of those four very specific signals, and now I've got not A, B, not C, D. Does that make sense? I think. So I've just used an AND gate to create a minturn. I'm going to take the next minturn, and I'm just going to use a different color, and I'm going to use another AND gate, but this one only has 3 inputs, so there also can be AND gates that exist that are 3 input AND gates. So I'm going to draw an AND gate. I'm going to put 3 inputs on that one, and then I'm going to feed in the correct values here. Let's say I don't need an A, I need B, so that's this wire right here. Right, I need what? C. And then I need not D. So that's coming off the inverter from D. And that creates that combination B, C, not D. All right, and then the last one, let's get a different color. There's only 2 there, so I'm just going to use a 2-input AND gate. Oh, I guess I can go ahead and, while I've got that color in my hand, I'm going to list that this is going to create A, not B. All right. And so A I need, bring A all the way down. And then not B, which I hadn't used yet. And there you go. That is what they meant by number 1. Implement each minturn in the logic expression with an AND gate with the same number of variables in the minturn. The previous activity, we traced inputs of A, B, C's, or X, Y, Z's through circuits and saw how going through the AND gate, you know, like an X and a Y into an AND gate, created the product of X and Y. So that's what we're doing. We're now drawing the circuit based on these expressions. Once you've created all the minturns, now we need to get them to all fit together to create the output. And the sum, the pluses, we use the word or. So it's I need this, or this, or this. As long as I have one of those combinations, I should have a true output. So I need an OR gate, and I'm going to assume that I could create or use a 3-input OR gate. So I'll have about 3 lines here, 3 inputs. An OR gate is like a kind of like a closed parenthesis on that side, and then it arcs as it comes to a point, those two. I don't know, it almost looks like a, what would that be? I don't know, just like an arrowhead kind of thing. So using the OR gate with these is going to create the final output of not A, B, not C, D, or this, B, C, not D, or A, not B. So we just have to feed these into the OR gate. And got it. I don't think that seems too difficult after what we've done. That seemed like kind of a natural progression. Using what we've already learned, it seems to make sense. We just hadn't actually done it yet. So this is taking the expression and making the circuit instead of doing it backwards, where we had the circuit and had to trace the letters through and make the expression. So you guys think that's doable? You think you got that? All right, so from here, I'm not going to give you, I think you'll need the time. Sorry, I'm turning to the wrong page. I'm not giving you like the assignment of like what to do next. I mean, if you get done with this activity and you're looking and ready to move on, I'll help you, kind of maybe point something out. But we should be, from yesterday, kind of spending the time completing this activity 212, AOI logic analysis. So you're really kind of doing circuit to table, and some problems are going from the circuit to the expression. So circuit to table is where we trace ones and zeros, all the different combinations of 1 and zeros, right, to find the minterms, to find the outputs that are 1. That gives us the minterms to write the expression. Or we can trace, instead of 1s and zeros through, we can from the circuit trace through the x, y, and z, or the a, b, c, and we can create the expression and then go to the table, right? You really want to follow the directions the way they do it. But once you get that done, if you just want to bring it up, we'll kind of compare real quick and see how you did. And I think that's going to take you most of the bell. If you have a little bit of time left, you could try to complete this problem down here, is actually rewriting this, but with a limitation that you don't get to use a 4-input AND gate. They say you have to only use a 2 or a 3-input AND gate. And for the OR gate, you can't use a 3-input OR gate. They say you have to only use a 2-input. And I think you guys, I'm happy to show you how if you struggle, but maybe see if you can figure that out. Okay?